Hi there, welcome back. Here's your screencast on forces. In this screencast, we're going to talk about springs, the difference between mass and weight, something called a normal force, and we're going to be introduced to free body diagrams. So let's get started. So forces, well, we can define that as a push or a pull. It is a definite vector quantity. Forces have direction. You can push or pull in a certain direction. We can represent forces with our vector arrows, just like we do for velocity. The unit is the Newton. And some sources of forces, well, we could have gravitational force, right? There's electric force, magnetic force, something called the nuclear strong, which is responsible for keeping the objects and particles in the nucleus together, and a nuclear weak force, which is responsible for some radioactive decay. So let's look at springs for a moment. Here we apply a force to an object tied to a spring, and if we pull on it, we stretch the spring. Not too surprising. But there's an interesting relationship, an important one, between the force that we pull with and the amount of stretch, displacement of the spring. If we plot the force against the displacement, the absolute value of the force, it would look something like that. So the more force you apply, the greater it stretches. Not only that, if you double the force, you double the stretch. This is a linear relationship. You could say that the force here equals some constant times the displacement. This is like y equals mx, where this k value here would be the gradient or slope. This is also called the spring constant. It's kind of a measure of how stiff the spring is. Let's talk about mass now. What is that? Well, it's a measure amount of stuff you have. That's a common definition of mass. It's also, mass is a other form of energy, and we'll study that if you go on and study more physics. But for Newtonian physics and forces here, we're just going to talk about mass as the amount of matter present. So if we have a lot of mass, we can be somebody big, or little mass, somebody small. It's definitely a scalar quantity. It has no direction associated with it. And the unit is a kilogram. How about weight? What is that, and how is it different from mass? Well, mass is you always have mass, but you only have weight when gravity is present. The equation, weight is the force due to gravity in this case, is your mass times your acceleration of gravity. This is a force. So weight is a force, mass is not. It's its own quantity. So weight is a vector quantity. Since it's a force, forces have direction. So for example, someone on the Earth would have a weight, and that weight would be directed downward. The units, as we saw before, the units of force is a Newton. So take an example. My mass is 75 kilograms. What would be my weight? Well, we use the equation. Force due to gravity is my mass times gravity. 75 times about 10 gives us about 740 newtons. So my weight would be 740 newtons. On the moon, my weight is around 120 newtons. Why is that? Well, it's a different gravitational constant on the moon. So the gravitational acceleration on the moon is about 1/6 of that on the Earth. So my weight would be about 6 times less. My mass on the moon, however, stays the same. That's still 75 kilograms. My mass doesn't change no matter where I am. One more example, in deep space. What would be my weight out in deep space, and why? Well, there's no gravitational field. There's no G out in deep space. So therefore, my gravitational force, or my weight, would be 0. So essentially, I'm weightless out there. Let's meet something called the normal force now. So if an apple touches the table, there's a contact force there. It's on the apple, and that is perpendicular to the table. So let's see a picture here. We have our apple on the table. We have this normal force is perpendicular to the table. So we have a right angle right in here between the force and the table. We also have the weight of the apple. So let's see some other examples of a normal force here. So here we have a ball on a table. Okay, we're going to use our free body diagram here to analyze the force on any one single object. And this is going to be important when we do this, because it's going to help immensely in our analyzing the dynamics of objects. So let's draw the force vectors. You have to include the direction, certainly, and we're going to find the resultant, or net, force on your object. So here we have force due to gravity. It's the weight of this ball going down, but there's also a force, the normal force, pushing up. And notice those two are equal and opposite, so they cancel each other, and there's no net force on this object. That's why it's at rest, and it remains at rest. This object here is flying through the air. Somebody's thrown the ball. It has a force on it, its weight, and that's it. That's the only force on that object. Over here, we have weight, which is being pulled straight down. But here the normal force is perpendicular to this surface, so it would look something like that. In this case, these two forces, as compared to over here, these are no longer balanced. So there is a net or resultant force on that ball. Indeed, it is aimed directly down the ramp. Let's have another example. Here's a mass hanging on a rope. What would the free body diagram look for that? Well, we have the tension going up and the weight going down. They're equal and opposite. Another example is a box at rest on a ramp. What would be the free body diagram for this box? Well, it looks something like this. We have the weight coming straight down as always. We have a normal force. It has to be perpendicular to the ramp, so that would be aimed this way. And then there would be a net force between just the weight and the normal force that would be pointing down this way here. But we know the box is not moving, so there's got to be a force this way to keep it from going down the ramp, and that's due to friction. So there's actually three forces on this box right here. Another example is some masses hanging over a pulley. Here we have M1 and M2. They might be the same, they might be different. The free body diagram for this situation would look something like this. We have the tension in the rope holding this box up. We have the weight of this first box, M1 over here, which is M1 times G. And likewise, we have the same tension, since it's the same rope, holding this mass up, and its weight down here is mass 2 times the gravitational acceleration. If you'd like some practice making free body diagrams, this link will take you there. I recommend you do that. And that's our screencast for forces. Hope that helps. Thanks. Bye.